Hello, I'm Hannah Donnert with the Collaborative on Health and the Environment. Change is bringing you the latest environmental health science through our partnership calls, webinars, science serves, publications, and social media. I would like to welcome everyone to today's CHE Partnership webinar, which is titled Suspect Screening, Prioritization, and Confirmation of Environmental Chemicals in Maternal-Newborn Pairs from San Francisco. Our moderator today is Cheryl Patton, Director of Commonwealth's Biomonitoring Resource Center. We'll leave time following this presentation for a brief Q&A session. You may type in questions to the Q&A feature available on the menu bar at the top of your window at any point during the presentation. After the presentation, our moderator will read out questions for our speakers to respond to. We'll get to as many comments and questions as we can during the Q&A period. For those of you who called in on the phone, we have posted slides to accompany today's webinar on our website. You can download these by going to healthandenvironment.org. Please scroll to the bottom of the page and select today's webinar. On the webinar page is a link to the slides. Everyone on the webinar right now is muted with the exception of our moderator and our speakers. This webinar is scheduled to last for 30 minutes and is being recorded for our call and webinar archive. With that, I'll turn things over to you, Cheryl.
Thank you very much, Hannah. And thank you everyone for joining this very important webinar. I'm really excited about it. It's on a new study that analyzed 30 matched maternal and cord blood samples from pregnant women in San Francisco and screened them using their non-targeted analysis workflow. A really remarkable new technique. It's really going to let us see what's in the human body, what kind of chemicals are there that haven't been characterized before. It's really opening a window, and I'm really excited about this new technology. Our speakers today, and I welcome them, are Dr. Dimitri Abrahamsson. He's an environmental chemist and a postdoctoral scholar at PRE, which is the program Reproductive Health and Environment. His research focuses on non-targeted analysis of biological environmental samples and characterizing human exposures to environmental chemicals. Before joining PRE, he worked as a postdoc researcher at USEP's National Exposure Research Lab in North Carolina and did his PhD in environmental chemistry at Stockholm University in Sweden. And I'd also like to welcome Dr. Tracey Woodruff. She's director of PRE, and Allison S. Carlson, endowed professor for PRE, and is a professor at the UCSF Department of Obstetrics, Gynecology, and Reproductive Sciences, and the Philip R. Lee Institute for Health Policy Studies. She is also director of a newly awarded NIHS Environmental Health Core Center grant. So congratulations on that, Tracey. That's really great. She has many other roles and many other accomplishments, and I'll leave you to go to our website, CHE's website, to learn more. But I wanted to point out that she is really well known for her innovations in translating and communicating scientific findings for clinical and policy audiences. She's the true pioneer in connecting science to policy. Quite amazing. So thank you very much for joining this call. So Dimitri, I'm going to turn this over to you now, and you can begin showing us your slides and begin the presentation. Thank you.
All right. Thank you so much. Thank you. I'm very excited and delighted to be here. Yeah, I wanted to share with you some thoughts about the work that we're doing at UCSF with non-target analysis and human blood samples. So let me start by talking about this concept of the exposome. This is a concept that scientists came up with when they understood the limitations of genetic variability to explain human disease. So there was a thought that there might be something else there, that human disease might be related to our exposures. And by exposures, we mean everything that we are exposed to. That can be chemicals, it can be any sort of pollution, it can be radiation, all the totality of our exposures. With recent advantages in high resolution mass spectrometry, we have the ability to screen biological samples for a very broad spectrum of chemicals, and we're able to detect chemicals that would previously remain undetected with traditional analytical techniques. These high-resolution techniques are applied in a fashion called non-target analysis, where we basically screen a sample without having decided a priori what chemicals we're going to look for. So that opens up a very important question, and that is, how many chemicals are we exposed to, and how many of these chemicals do we know about? So if we have a look at the numbers a little bit, we'll see that, for example, when we look at the Toxic Substances Control Act, the Chemical Substance Inventory, lists about 80,000 chemical substances in total, out of which 40,000 chemical substances are actively used in the United States. It's important to note that the inventory does not include pesticides, it does not include food additives, drugs, cosmetics, tobacco products, nuclear materials, and munitions. What's also important to know is that the EPA's CompTox chemistry dashboard lists about 900,000 chemicals known to have some environmental relevance. Now, these include chemicals not only used in the United States, but chemicals that may be used in other places and may be also imported into the United States as we import products from other countries. The work that we do at UCSF focuses on pregnancy and focuses on this period of development that is a critical period of development due to the unique susceptibility to biological and chemical perturbations. So I wanted to spend a minute to talk about one of my favorite movies, and that's Dark Waters. I'm sure many of you have seen this movie. If you haven't seen it, you should absolutely go see it. Mark Ruffalo is incredible in that movie. One interesting aspect that comes up is that chemical manufacturers in the United States are allowed to self-regulate. Now, the movie shows a situation a few years back, so things have changed since then, especially with the new chemicals program under TSCA. But what is the key point here, I think, is that there's certainly a higher degree of self-regulation in the United States for chemical manufacturers compared to other places in the world, let's say the European Union, which has more stringent criteria when it comes to releasing chemicals to the environment. Now, another super interesting movie, it's more of a documentary, The Devil We Know, talks about the same story with the PFAS contamination in the United States, and especially in the states of West Virginia and North Carolina. And one interesting aspect that comes up during the documentary is that towards the end, when they're doing the epidemiological studies and they're trying to establish the evidence and try to establish the link between the PFAS exposure and the diseases in the area, the epidemiologists are trying to find people that have not been exposed to PFAS. And in that search, they try to find people that live in isolated places in the South Pacific. They try to find people that live in places that don't necessarily have the latest Teflon pans. And to their surprise, there's actually not a single person on the planet that doesn't have PFAS in their blood. So that is a fascinating story, because if that is the case, then they're unable to find control samples. And the only samples that we're able to find to use as control samples were blood samples from a blood bank in the Department of Defense from veterans that gave blood samples before the Second World War. And that was before PFAS was released. So that's an interesting point to know that these exposures are universal and we're all exposed to them. And I don't think we've signed up for that. Now, when looking at chemicals and studying chemicals in general, one of the hurdles that we face is we try to, trying to identify these chemicals with analytical standards. And there are certain limitations to that because chemical manufacturers don't always make standards available. One of the most recent stories was with Solvay, and their specific PFAS that they're releasing from their plants, they had made available that standard through a commercial lab called Wellington Labs. And at some point, they decided to discontinue their license to Wellington to produce that standard. Now that created a huge storm on Twitter with scientists, environmental chemists, environmental scientists, and epidemiologists talking about this as a very dangerous precedent for chemical manufacturers, and what that may mean in the future, chemical manufacturers may not, if that goes through, who's to say that chemical manufacturers really need to release, the structures and the chemical standards that for the chemicals that they're releasing in the environment. And if they don't, that creates a huge obstacle for scientists to identify these chemicals and to measure these chemicals in environmental and biological media. So more specifics now, talk about our study. We collected 30 maternal blood samples and 30 cord blood samples, and we analyzed them with a technique called high-resolution mass spectrometry. This is a relatively recent technique in mass spectrometry, and its application, especially in non-target analysis and in the analysis of environmental pollutants, is even more recent. So just to give you an idea of what the workflow looks like, we start by collecting the blood samples. We extract and we do minimal cleanup for these samples. We analyze them with an instrument called liquid chromatography, quadruple time of flight mass spectrometry. It operates in two different modes, in electrospray ionization in positive and negative modes. We analyze the samples in both modes. We get the data from the instrument, and we do something called feature extraction and alignment. And then when we get our peaks in the chromatogram, we assign specific molecular formulas to the masses that we detected in our samples. Then once we've assigned molecular formulas, which is basically, how many carbons you have, how many hydrogens, how many oxygens, but it doesn't really tell you much about the structure. It just tells you about the composition of the molecule. What is the molecule built of? Then, once we have that information, we can go on and do more targeted mass spectrometry fragmentation experiments, where we can start building on the diagnostic evidence of the molecule and looking at the fingerprinting of the molecule and how that fingerprint matches spectra that we have in experimental and in other online in silico databases. And the final step is trying to confirm the chemicals that we detected with analytical standards. That's the highest confirmation standard. So just to give you an idea of the steps that we followed, because we're interested mainly in features that are in chemicals that are we're exposed to at a very high frequency. So we're interested in chemicals that most people are exposed to. We look at, we start filtering our data set by looking at only the features that appear in 100% of our samples. And then from 100% of our samples, we also look at, we go to the detection frequency and rank, and we look at the chemicals that are at the top 50% when you're looking at the abundance of these chemicals in the samples. Another criteria that we applied is we wanted to focus on chemicals that show some interesting differences between maternal and cord blood. And that these differences were, for example, if the chemical appears to be at a higher concentration in the maternal blood, if it appears to be at a much lower concentration in the maternal blood, or if there's a very strong correlation between maternal and cord blood. That allows us to focus more on chemicals that may have something to do with maternal and cord partitioning. And finally, the final criteria we use is demographic variables. So we try to filter out chemicals, or we try to keep chemicals that show some differences with respect to demographic variables. And that's more to allow us to look at in-just exposures, to allow us to look at chemicals that may have something to do with disadvantaged groups, demographic groups.
Apparently you're right, Dimitri.
Excuse me?
Nothing. So that deserved a song when you said that.
Oh, thank you, Tracey. Once we collected all that information from these criteria, we'll look at whether these chemicals have been previously biomonitored by Anne Haynes, or they're present in any other pharmaceutical lists, or they're likely to be endogenous chemicals. And so what we're trying to do here is basically we're trying to remove features that people already know about. Since our workflow is primarily focused on discovering chemicals that we don't know about, we want to make sure that we remove things that have been previously reported and are well documented. And our final steps include, as we mentioned earlier, include mass spectrometry fragmentation analysis to confirm, or not confirm, but to build the diagnostic evidence for the molecule for as many chemicals as we can. If we cannot get enough information from the fragmentation analysis, we also have a prioritization algorithm that helps us to sort out specific isomers for a given formula, and then rank these isomers from most likely to less likely, and get an information as to what that molecule might look like. And our final step is confirmation with analytical standards. So just a rough idea about the numbers. We start with about 208 features, and then we go to 73 features confirmed with MS. Then we have 45 features that we have some diagnostic evidence on based on our algorithm. And then finally, we have 17 features and 15 unique compounds that are being confirmed with analytical standards. This is just a slide to sort of illustrate the point of demographic differences and how these differences are manifested in between maternal and cord blood. So for example, when you look at race and ethnicity, and it's like self-perceived race, or how people identify as, you can see that there are certain features that appear to be significant in the mothers, but these features don't necessarily show the same trend in the cord blood. The same goes for education. If certain features appear to be significant in the mothers, meaning features, let's say, that appear to be significantly enriched in mothers with lower education or higher education, these features will not necessarily show as significant in the cord blood. Same for household income, same for nativity. This is an interesting idea because it sort of makes us think that how chemicals partition and how they behave has something to do also with their physicochemical properties. So if something appears to be significant in the mothers but not in the babies, that might have something to do with how the chemical crosses the placenta from the mother to the baby. So, we know that not all chemicals are efficient at crossing the placenta, and we know that some chemicals are very efficient at crossing the placenta. A little bit more information on the confidence in confirmation when we're talking about compounds from non-target analysis, just to give you an idea of what we're dealing with. So we start, let's say, with level 5, and this is just this is a schematic representation of how we can communicate confidence, and it comes from a study of it's from a paper. It's not exactly a study, it's a communication paper of Szymanski et al. It was published in Environmental Science Technology in 2014. So we started with level 5, which is basically the exact mass of interest. We started with just looking at the molecular mass that we detected in our instrument. We don't have any more information on that, just the molecular mass. Then for some of these masses, we'll be able to assign molecular formulas, which will give us information on the composition of the molecule, how many carbons, how many oxygens, how many nitrogens, and so on. Level 3 goes more into tentative candidates. And these are candidates that may come, let's say, from a prioritization algorithm, where you have some diagnostic evidence on that molecule, but that evidence may be relatively limited. And then you have level 2, which goes more into the probable structure and the mass spectrometry fragmentation analysis. And then finally, level 1, the confirmation with analytical standards. These are a couple of figures that I wanted to show you. These are from the results of our study. So when looking at the sources and uses of chemicals in maternal and cord samples, if we look at all compounds, for example, that we detected, and we try to see where are these compounds used and what can we know about their sources and uses, we see that we have a pretty large number, about 40 chemicals that are used as plasticizers. We have about 30 chemicals that are used that are known high production volume chemicals. We have a good number of pharmaceuticals, pesticides, cosmetics, and a limited number of PFAS. And you can see here the different levels of identification or different levels of confirmation. And you will also see that there's a really big number of chemicals that are unknown. So, and by known, it just means that we don't know where exactly they're being used and what their properties are. Now, when we filter out all the chemicals that have been previously reported, and we do that by searching large databases that report all chemicals reported in blood samples in previous studies. So when we filter these chemicals out, we see that there's a very big number of chemicals, about 30, almost 40 chemicals, for which we have very little information about. We know what these chemicals look like. We have some good sense of their structures, but they don't fit in any of the categories that we search. And this is an important message that we wanted to get across, that there is a need for for manufacturers to really, I guess, work closely with EPA and environmental agencies to detail the uses of their chemicals, because we know that we're being exposed to chemicals that we can see their structures, but we don't really know what their uses are and where they're coming from. So to give you some examples of what these chemicals look like, you can see, for example, the top left, we have a chemical that is used in consumer products, personal care products, and fragrances. We have another chemical on the right side, Sumilizer GA, that is used as a plasticizer and in the production of plastic polymers. These are chemicals that appear to have very limited information on their uses and appear to not have been previously reported in human blood samples. We also found some interesting PFAS that are not your very well studied PFAS. We found the one on the left here, that is a PFAS that is thought to be an impurity of PFNA. It probably comes from the manufacturer. It may be an impurity during the manufacturing of PFNA, and it's also a breakdown product of long-chain fluorotelmer based products. It's interesting that that chemical appears to not have been previously reported in blood, most likely because it's an impurity. And when people study chemicals in blood, they don't really study impurities in the composition. They study the main chemical used in composition formulation. The one on the right is also another PFAS that appears to not have been previously reported, most probably derived from long-chain fluorotelmers, and as most PFAS is used as a surface protector for textiles, food contact materials, carpets, and so on. So, and here's my final slide, and I think that's where I'd like Tracey to come in and help me out with this one. So a few points that we wanted to bring up as conclusions is that non-target analysis and suspect screening methods are valuable tools in uncovering previously unknown exposures. And I think we sort of made a good point with our study that, we're able to see chemicals that would previously go undetected with traditional targeted techniques. These findings hopefully can be used to inform biomonitoring studies and toxicity testing. Since these chemicals are not so well studied, there's a ton of information that we don't know about what their levels are like in the population, and we also don't know what their toxicities are. There are numerous chemicals that we're exposed to but remain unknown. We're basically, with our study, we're just scratching the surface of it. There's so many more features that have not been identified. There's so many more features that need to be further characterized. And then one important hurdle in moving forward with these studies is the limited availability of analytical standards. And that is an important roadblock that prevents scientists from confirming many chemicals and quantifying their levels. And I think the last most important thing that I wanted to mention is that the US, in my opinion, the US EPA needs to request analytical standards from chemical manufacturers for all chemicals in the market. This is something that cannot be left to private companies like Wellington. It cannot be left to manufacturers to make available their standards if they want to. These chemicals, if they are released to the environment, need to be made available to researchers. So I'm just going to stop there. I'm going to leave it on. I'm going to pass it on to Tracey.
Thank you, Dimitri. I just wanted to emphasize a few points about this study that I think are important to that highlight how far we've come in terms of using this suspect non-targeted analysis approach, because it has been a number of years that we started on this. And one thing that is really moved the field a lot is the availability of new software tools and databases. So the Computox, the dashboard, the EPA's chemical dashboard wasn't actually available when we started, and now they have such a wealth of chemical feature information that allows us, that is the next step in terms of being able to scan for these chemical exposures. The other is that there's new software tools that are now available. So when we actually in the middle of this research project, we used the available software tools from Agilent and identified some number of features, but by using newer tools like this MS Dial that allows us to scan more for the features, and also some analytic chemistry techniques we can talk about in the Q&A. We actually identified almost 100. So the breakdown of you saw the graph which showed the different bar charts, but it's about 100, a little over 100 new chemical features. And I just want to remind everyone that we actually used a pretty strict filter to get there, right? You had to be detected in all the samples, not biomonitored in NHANES, and then a few other things. And also, I think Dimitri did develop these techniques to allow us to identify more level 1 and 2, which is kind of like causal and probable. That would, like, if you're thinking about it in the human health world. So I think those are some. So I think this, by developing this workflow, we have the capacity to expand it to a broader range of samples. And this is part of a larger study that has 300 matched maternal cord blood samples. And then the last thing I wanted to say about this is that, no, I think those are the kind of the key features. And then obviously it just illustrates how much we really need to do to have the chemical manufacturers tell us what all these chemicals are that they're using and where they're used. And as you saw, there was a large portion of them that we have no information on where they're being used. And probably the information we have on the ones that the categories of where they're being used are probably not highly accurate, knowing how EPA is very limited in their ability to collect information about chemical usage, particularly for chemicals that are already existing on the marketplace. So.
Okay, thank you very much. So we could go into questions and answers now. We have just a little bit of time. Did you do any kind of exposure questionnaire surveys with the people that so you maybe have a sense of what they were all doing or products they were using, anything like that?
We did have an exposure related a questionnaire survey. Do you want to talk about that, Dimitri? I would say we're at the beginning stages of trying to determine.
Right.
It's something and everything that's influential in some ways, but go ahead, Dimitri.
Yeah, so we have, that's right, we have very detailed questionnaires about what kind of products people are using and how many times they're using them per day. If they, for example, they have done any, if they applied any chemicals to their furniture or carpets, if they have reinstalled some kind of floor in their house. So, and I can give you a little teaser about some preliminary analysis. We see that some of the chemicals that we detect come from furniture and carpets, and from what you call it, like a toaster. It's like a George Foreman toaster. And they also correlate very strongly with how old that application is. So we see, for example, higher levels in people who have had a toaster for a very long time and it has multiple scratches.
Oh, so anyway, I just want to thank you for the presentation before we go too much further. That was probably one of the best explanations of how this technology works. So thank you very much for that. It's certainly going to go into my library to look at again, and then call you over more questions about say what. This is really, really good. Thank you for that. But I think the policy implications are pretty amazing. What kind of response are you getting from EPA or the people at TSCA or even IRIS about what you're finding and how they might want to incorporate some of your recommendations and how they move forward and looking at these chemicals?
Well, they asked for a copy of the paper. One person did in the TSCA office. We haven't really heard too much from EPA. I think this is the kind of something where, first of all, there's they're very busy trying to work on already the well-known existing chemicals that we know about, like methylene chloride, TCE, and perchloroethylene. So I think the idea of trying to determine what to do next in terms of the TSCA kind of program, I think is that's something that they will probably have to think about. But I do think this idea that Dimitri talked about in his talk, which is there's certain kind of fundamental things that EPA could request from the chemical manufacturers that would allow us to at least monitor for these chemical substances, like the analytic standards. And it wouldn't really, it shouldn't be hidden by the confidential business information, right? The CBI, trade secret, because the reality is these chemicals are being used in products and they don't stay in the products. I think that's another theme that you see over and over again in these studies is that, what we're told is that the chemicals are inert, they stay in the product, they don't get out, but that's obviously not true. They're getting out and about and getting into us. So I think for us, we're mulling through what would be the right approach for this. I mean, there's so many fundamental issues about this, like requiring disclosure of where the chemicals are used, the chemical standards. We have to think about, well, when we're making comments to EPA about the best way to use science and TSCA implementation, what should they be doing? The other area that EPA is investing in is computational toxicology. And so I think the dashboard that they've been investing in probably over the last, I don't know, maybe 4 or 5 years, maybe a little bit longer than that. I think that's a really helpful tool for us. And so we want to support EPA in continuing to invest in that because we think that's going to help, provide infrastructure support to the research community to work on these types of issues.
And for getting into dashboard and utilizing it, was that a complicated process? Was it something easy to learn? Is it accessible that, NGOs or government officials can dive in and try to work with it?
Yeah, I think it's a fantastic resource, and they have lists of everybody's list. So if you want to know the Stockholm list or you want to know European list of PFAS or whatever, they try and keep an updated list there. The only thing about it, it's a little slow when you ask it to do something, but I don't know.
That's
probably
right.
because they're searching for 900,000 entries. I don't know, Dimitri, you want to comment about it? I love the dashboard. I'm a big fan, so.
Yeah, I love the dashboard too. I think it's fairly easy to access. And it's fairly intuitive. So I think even if you don't know, if you play around a little bit, you'll figure out how to get the information you're looking for. Yeah, that's what exactly what I was going to say, that it's just a little bit slow. So I hope they find a better server. So
they really need to access a supercomputer. Once they do that, it'll be like so awesome. But I mean, that's the kind of thing you want the government to do: provide information, aggregate all the information that's out there in an easily used, searchable database. So I really just think it's a great resource.
I think there are people in EPA completely agree with that. They have this information. Let's get it out so people can see what's happening. So I think kind of study is really going to support that. I'd looked at, your 2 PFAS chemicals. I tried to count quickly. I think one was C8, one was C10. So those are long chains. So they'll be bioaccumulative, right? So are you doing any kind of follow-up with the samples? Because I don't know about the other chemicals, but you would expect the level of those possibly, depending on exposure, to increase and stick around in bodies, right?
We're certainly looking more into that. One interesting aspect that we thought about, and it came up from a conversation with Ian Cousins, who's a a famous expert on PFAS, is that because we see these chemicals being transferred to the fetus, and if they are transferred to the fetus, they're not only bioaccumulative, but they will remain in the population for a very long time as they're being transferred from mother to daughter, from daughter to next daughter. So that is an interesting complication with these chemicals that we're not going to be done with them anytime soon. As I said, we're also looking more into what are these chemicals doing to our metabolisms. And even though I haven't really presented any results on that from our extended study, where we look at 300 samples, 300 maternal and 300 cord samples, we see some interesting correlations with these chemicals and fatty acid metabolism. And this is something that's been reported in a couple of previous studies before, recently. And it sort of points to the idea that they might be interfering with our metabolism, and it might be connected to certain diseases related to lipid metabolism, like diabetes, for example.
That's really.
But I think to look for those particular PFAS, those impurities, we'd have to have a chemical standard to completely confirm it. Though I think those are probably, because they're more unique. They don't have isomers. Probably sure there, but the levels. So I don't know, Dimitri, but probably there is, I don't know if one of the things that we've had a challenge with, and I would suspect it's going to be hard to get a chemical standard for those, because we also have a work that we're doing with Dr. Jennifer Fung, who's at UCSF, who's been testing chemicals that we identify in a yeast assay to test for reproductive toxicity effects. And one of our challenges has been, again, going back to like availability of being able to evaluate these, it's hard to find these chemicals, and even the ones that we know, and purchase them from sources within the United States. So I think that these ones that we've identified in this study are very likely going to be in this group that probably aren't readily available for us to get a standard for.
Okay, thank you for that. I'm glad you're following up, doing some follow-up. We have a bunch of questions, and so I'm going to try to quickly pick some out here. Sue Fenton said 2 plasticizers that were not reported previously. That she said that's really disturbing. Any idea what they might be? And are you talking to Ann Haynes, analytical chemist, to see if they have seen these or may have tested for them in the past, but were low detect back then when he did the kind of testing? She's talking about the plasticizers.
That's a very good point. We would love to get in contact with analytical chemists from Ann Haynes and see, if these chemicals have been found before, but maybe not reported, because at least from what we can see is that they appear to not have been previously reported. So, but we want to absolutely work more on that and connect with these people to see if they were found.
Okay, and then Isabel Plant, by looking at the top 50 chemicals, you might miss some chemicals that are less abundant but more toxic. Is there a way to look at those that are less abundant but might possibly more toxic? Do you have a sense of how you might do that or think about that?
Tracey?
That's
how much should we
true.
say? I don't know how much we can reveal. Okay.
But we do have some ideas about, this is Dimitri, we could take we are thinking about ways to use the extract from when you process the samples for doing the analytic chemistry portion, to test those in our in vitro test system. So it's possible we could look at the mixture as extracted from the blood sample. There's a lot. That sounds very simple. There's some technical features to this that would have to be done, but that's one option to try and assess the toxicity. Now that we have the extract, we have like I said, we have work with the lab that's doing yeast, also C. elegans, and I think she's trying to get into zebrafish. So we have more of a complementary set of in vitro testing that we could use to evaluate it. So it's possible to do this.
Cool, that's great. Someone anonymous is, so does this mean that of the 40 chemicals used in the US, there are only 40 unknown ones that you found in people's bodies? Or does this mean that you found 40, but there could be hundreds or even thousands more chemicals that have been uncharacterized in people's bodies?
I would say we're just like scratching the surface of it. We don't really know so much about, the fact that there's such a discrepancy between the numbers, and that was something that I wanted to introduce early on, that, we know that there's 40,000 chemicals that are actively used, but the dashboard has listed about 900,000 chemicals. So it's very hard to know, where are we? Are we in the 900,000 ballpark, or are we in the 40,000? And how many of these chemicals are maybe not used in the United States, but are actively being imported in the United States from countries that don't have the same regulations and don't have the same lists as we do here. So I would, anything I say would be a guess, but if I make an educated guess, it would be that we're just scratching the surface, and I'm sure that there's a ton more chemicals that remain uncharacterized. That could also be just, plain metabolites, like how chemicals, you're exposed to one thing, but it's biotransforming in your body, becomes something else, and may not have been as toxic in the beginning, but then the transformation product is a lot more toxic. So we need to have a look at these too. We know maybe even if we are in the 40,000, these 40,000 will produce, a ton of metabolites. So we need to have a look at these too.
Yeah, I just want to also point out that Dimitri talked about the Tosca inventory, but there's a really interesting paper that came out last year. I think it was in ES&T that actually aggregated all the chemical inventories globally, and said there were 350,000 chemicals that are registered in some country in the world. So I would say, yes, you have this transformational impurities issue. You have 350,000 chemicals that are registered for use globally. The 900,000 is not inconceivable. So that we're talking about, like, 30 match samples where we filtered down our criteria. So it's a good hypothesis. A reasonable hypothesis that we're going to find more once we expand our technology capacity.
Thank you for these great answers. And I think there has been some questions about whether what you were finding were metabolites or actual parent chemicals, but I think you've answered that. Here's I think we probably have a time for maybe just one more, and this is for Tracey. I'll just read it out. Anonymous. There is a returning phenomenon. Some pollutants are higher in newborns' cord blood and urine than in their mothers in serum urine, for instance. And the examples are glyphosate in urine, blood higher in younger children, BPA, some phthalates. What's the reason for this phenomenon? And then what does this mean in terms of development of diseases later in childhood or adulthood? But basically, they're wondering why there's this difference in concentrations.
So I'm going to answer the first part of this, and then I'm going to turn over to Dimitri, because he's been looking at this issue from a chemistry's perspective. But I would say because we've actually been interested in this topic for a number of years here at UCSF, and we've been looking at it in the prenatal stage. So some of our hypotheses are that, we know that chemical exposures during pregnancy can be at one level, and it can be higher or lower when you measure it in infant cord blood, or when you measure it during the second trimester. A chemical, it's like a pollutant that we know that bioaccumulates in the infant is methyl mercury. Another pollutant we know that doesn't appear to pass the placenta too well is cadmium. But I would say in general, they're within a factor of 2 for what we're measuring, though there's some important things that influence that. I would say, though, in childhood, like infancy and toddlers, you're going to see exposures that may be much higher than the mother, and that's because of behavioral activities, right? Little kids crawl around on the floor. Chemicals love dust, so they're hanging out in the dust, and the kids get in the dust and put their hands in their mouth. And there are studies showing that exposures in young children can be much higher because of that. So there's the biology that influences this, as well as the behavior activities. And I'm going to let Dimitri talk a little bit about it, because we actually are finishing up a paper where we explored this issue a little bit more. And actually, he's been doing some work on this related to PFAS, because I think the answer is there's multiple answers in this. So I'll let you talk to Dimitri, and then I'll follow up.
Okay.
Yeah, this is a very interesting topic, and we've been exploring it for some time now, but we also realize that it's a very complicated topic and it's very hard to come up with definitive answers. Well, and even if you just have a look at the literature and how people have tried to, especially in pharmaceutical chemistry, how people have tried to study the transfer of drugs from the mother to the fetus, you'll see that there's a variety of studies that report relatively inconsistent findings about what are the properties that determine that partitioning. But what we can see, at least from our data, is that this is something that seems to be determined by both the properties of the chemical, but also by the properties of the chemical's environment. And in that particular case, the placenta and how that membrane is developed in during pregnancy. So we see that there are actually differences in early birth versus late birth. There are also differences between gestational diabetes moms and moms without gestational diabetes. And we see very specific trends between very hydrophobic chemicals and very hydrophilic chemicals. We see chemicals that like to be more in the fat tend to be more in the maternal side versus smaller molecules that like to be more in the water side can go through the placenta and go to the fetus. But it's not that we're explaining 100% of the variability. It seems like we're just basically just figuring out what are the parameters influencing that behavior. But it seems that there's actually a ton of things that that work together. So yeah, it's a very complicated issue, but it's very interesting. We're trying to figure it out.
Okay, thank you very much. One last request was for someone to post the link to dashboard. We have a lot of people that want to.
Oh yes, absolutely. Yeah.
So we're going to need to close now.
Remember, it's slow.
Yeah.
You might go get some coffee while you're waiting for it to find your chemical. Pick something really popular.
Okay, Hannah's giving me the high sign here. We just want to remind everybody that this is a partnership webinar from CHE and the EDC Strategies Group. And if you want to know about EDC research and legislative activities in Europe, please contact HEAL. They have a website and you can join their listserv. And for EDC's work here in the United States, Jerry Heindel and Sarah Howard also have a listserv that you might join. And that information for this now is on the site itself, the PowerPoint itself. But thank you guys both for participating. I had a great time asking you questions, and the answers are just wonderful. And just thanks so much for the work you're doing. This is really the best, the very best. So thanks again.
Thank you
so much for inviting us.
Thank you, everyone, and Hannah.
Yeah, great. Well, thank you so much, Cheryl, and to Tracey and to Dimitri. We're approaching today's and the end of today's webinar. A video recording will be available on CHE's website soon, and tomorrow you'll receive an email containing a link to the video. The next CHE AK partnership call will take place May 26th and is titled Mercury, Fish, and Public Health Concerns, the proposed Donlin Gold Mine. To learn more and to RSVP, please visit our website at healthandenvironment.org. If you are new to CHE and would like to stay updated about upcoming events or more, please sign up to receive our newsletter by selecting the Join Us tab at the top of any page on our website at healthandenvironment.org. Additionally, if you appreciate these CHE partnership webinars bringing you the latest environmental health research for free, we encourage you to support CHE's ongoing work by making a tax-deductible donation via our secure website. Again, our website is healthandenvironment.org. With that, I would like to thank our speakers, Dr. Woodruff and Dr. Abrahamsson, for taking time today, and to you, Cheryl, for your excellent moderation. Thank you so much for joining us. Have a great day and take care.